So I guess my task today is to try and give you a bit of an oversight of PHOENIX RapidFire. And I guess I've called PHOENIX RapidFire a bushfire characterisation model rather than necessarily a fire behaviour model, but inherently it does model fire. And some acknowledgements up the bat. Straight off the bat, I guess, is Derek Chong, who's been the primary co-driver and major input into the development of this process. Tom Duff, Brett Surlis and Alistair Pitts have all had major inputs, and it's been funded through the Bushfire CRC, DSE and the University of Melbourne. So PHOENIX RapidFire is really a mechanistic, dynamic, continuous, empirical fire behaviour model. It's mechanistic because every time you run it, providing the inputs are the same, you'll get the same output. It's dynamic because the way in which we incorporate the fuels, the weather, the terrain, really depends on what happened in the previous time step and in the previous perhaps even an hour or so before the fire got there. So you're not necessarily going to get the same calculated value at every point in the landscape every time you run the model. It's continuous because the fire perimeter is spread continuously across the landscape, even though we have these little cells that you'll see there. Those cells are for input and output data. So it's not a cellular autonomous model. And it's empirical because what we've really done is put a whole lot of our understandings of how we think fire behaviour works, a lot of concepts together, and then we've basically developed some ways of trying to quantify that. And I'd have to admit very freely that the mechanisms and some of those parameterisations are up for discussion and debate. So we've tried to put a model together the best way we understand how fire behaviour works, even though we don't have a lot of necessarily experimental or primary data to support that. And that's where some of the work we've heard earlier this morning and in previous days is going to be fundamental to basically improving a model like PHOENIX. So what we do in PHOENIX, and the first thing, piece of information we need to know the ignition time and location. And that will determine initially what the weather's like, what the fuels are like, what the terrain is like. And surprisingly, that's often incorrect, and if we're using it in an operational sense, and that's our first source of error. But what we've basically done is taken information, GIS type information, spatial information, that's originally at a 30-metre resolution, and then we've aggregated that into a particular cell size, which typically we run at about 200 metres. And then we look for the nearest weather stream. And the introduction of gridded weather forecast has been fabulous for us. One of the first tools that was able to use that data really was PHOENIX, because it was able to basically capture that complex, massive data sets. The second part of the process really is trying to deal with what Jim has just described here, that initial build-up phase. So what we do there, basically, we look at what the, if you like, the quasi-steady state rate of spread might be, work out the length to breadth ratio for that location, and we have this fairly arbitrary multiplication factor of 3.5 times the length to breadth ratio to give us the length of time we think the fire would take to build up, and then we scale using one of those curves that Jim showed earlier. We scale both the time interval as well as the wind speed according to where we are on that build-up phase. So the build-up phase could be a few minutes, a couple of minutes, or it could be an hour or more, depending on that length to breadth ratio. So we've got a function in there. Whether it's right or not is very much open to debate, and we'd be more than happy to put a different function in there if we had something better, and so we're looking to Jim eventually to get that better. But at least we've got the concept of that build-up phase present. So to look at that in the modelling sense, in the first few minutes, we basically just run the model in this build-up phase, and what we can see in this little video here is we might be running the model every minute or two to get that build-up phase. What we can see here, this build-up phase has taken about 45 minutes, and you can see the width of the fire there happens to be about 120 metres. These spot fires that have also built up, 80 metres for that one, and this one's about 75 metres, I think. So we're trying to generalise some of these characterisations. So using the fuel, the terrain and the weather that we've got at a location. Next, we look at the perimeter of the fire, which is divided into a whole sequence of points. And the trouble with points, they then have to be joined by segments, which is an inherent issue that we deal with. But for each perimeter point, we basically start with the windwardmost perimeter point, so at the back of the fire, if you like, and work clockwise around. We calculate the flame height that we might get from that based on the weather and the combined near-surface fuel load, and then ask ourselves, is that sufficient to start to incorporate the elevated and bark fuels? And we progressively incorporate those, and in this case, until the average flame height gets to 2 metres. Then we calculate the rate of spread at that point, the flame height, the intensity, basically using the general MacArthur model or the grassland, CSIRO grassland models. And that's done for every point around the perimeter. So you might have several thousand points around a perimeter, and each point will be different because it's experiencing different wind, different fuel, and so on. So the head fire, you might be incorporating perhaps the whole fuel complex, but towards the back of the fire or the flanks of the fire, you might only be incorporating the surface fuel component. We use PHOENIX spread algorithm to determine the spread distance and direction. That's basically come from the CSIRO fire application of that, which seems to be a better implementation than what has been used in Farsight and Prometheus. Just the mathematics are a little smarter in a way. And then we repeat that for the next perimeter point as we go around the perimeter. So we're dynamically looking at the fuel, the weather, the terrain as we move around. Following that, we start to look at all those perimeter points, and then we take the hottest 25% of those perimeter points, wherever they happen to be, and then start to aggregate them, starting with the hottest point, and then seeing whether or not it's hot enough to actually draw in its neighbour. And we go through a process to identify the heat segments. They're the white areas shown up here, and those heat segments are then grouped into convective centres. So on the left here we can see areas where the three spot fires, the heat centres are independent of each other. But as they grow, there's a potential for coalescence of some of these heat centres, so they're convective coalescence, even though at the ground, at the surface, the fires are still separated. And then it's possible for these to aggregate. And so we combine the total amount of heat output coming from within that footprint of that heat centre. So what we do is basically, once we've identified one heat centre, we'll then look at the remaining hottest 25% of the points and keep going around the fire, acknowledging that there could be many heat centres. So those bubbles you saw coming up from that very first video that I showed are coming from these heat centres. So the diameter is showing the area, and the size of the bubble showing the amount of heat that's likely to be involved in that. And this is not a Will Thurston type modelling process. This is a very rudimentary understanding of what the convective process is, but we're just trying to capture the magnitude of that convective component to some extent, because we know how important it is. So we use that convective heat output as a driver for our spotting. I'll come back to that. So spotting is a major component of our fire behaviour model. So we've basically considered that there's both a flame front propagation, but an important aspect as well is the presence of spotting. So with spotting, we use those convective centres to look at, well, within that footprint, what's the amount of bark material, assuming that the majority of the embers are coming from bark. Then look at the amount of heat that's coming out from that convective centre and work out a travel time, how long it's going to be buoyant in the air for. So that gives us a hang time, as Derek calls it. He's a bit of a water person. The embers are then transported according to the speed and direction of the surface winds, which we know is not really right. but we've had difficulty getting a good transport wind in any other way, but it's what we're using. And the ember distribution then is determined in both in the path that the embers are travelling away from the fire, as well as perpendicular to that path. So in the distance away from the front of the fire, we have a bimodal distribution with distance, and across the path we have a normally distributed ember distribution. So basically what we're doing, we've got a function up here which determines the amount of embers that are likely to be available based on the amount of bark that we've got present. Then the proportion of those embers that might be launched will be determined by the convective strength that we have present, and then the convective strength will also determine the hang time, how long those embers are likely to be in the air. Given the wind speed and direction, we can work out where the maximum distance they're likely to land. So this is just showing the bimodal distribution that we use. So what we see in the different coloured lines basically are lines for different hang times, which are associated with different convective strengths. So what we have down on the left-hand side here is where the embers are being dropped largely with an exponential drop-off rate, which are mainly being driven just by the surface winds, if you like. So it's a wind-driven sort of spotting process. But as the convection builds up, we actually get the potential for embers to be dropped at some distance downwind. So we do get it, it's a bit flat here, but we do get embers dropped in between there, of course, but there is also a peak in the drop-off. So we try and capture that sort of bimodal distribution of embers, so the convective-driven as well as the wind-driven embers. We model the spotting process separately. We do it in a 200-metre grid, so we don't really consider what's happening in the first 200 metres. We consider that to already have been incorporated in the fundamental spread of the fire in the surface spread models. So what we do is basically look at all the cells downstream that might have been impacted by embers, and then aggregate how many embers have landed there, look at the fuel moisture. Here we actually use Stuart Matthews' fuel moisture model because it's more accurate than the MacArthur relationship. And we basically, once we get to a probability of 1 in terms of the ignition probability, we'll start a fire in that cell. And it's only once we get to that point. So we recognise that there could well be spot fires elsewhere, but the probability is too low for us to actually start it as a new fire. When the ember falls into grass, we assume that we're going to have a 4-time increase in the probability of the spot fire starting. So spot fires will start more readily in grassland than they will in a forest. Where does 4 come from? Well, we'd really like to have some better basis for that. Miguel's working on that, Miguel. So the ignition probability you'll see here is a function of the fuel moisture content. Surface fuel moisture content, that's where we're using Stuart's model rather than the relationship out of MacArthur, because we get the radiation, we get the slope and wind effects incorporated into that. Then the spot fires are started as an independent new fire. So we're not modelling one fire as such, we could be modelling 2,000 fires in a large fire event. So we've got a number of significant spot fires as well as the main fire area, and they're all being modelled at the same time. There's an artefact that comes out of using Huygens, and that is because we've got perimeter points with a segment in between, it's possible for those points to get out of step to some extent, and you can end up with what looks like a tangle effectively in that perimeter point. So there's a need to go around the perimeter every time step and get rid of those tangles, and at the same time look at whether or not the main fire has encountered or run into an existing spot fire. And if it has, you then basically add it into the main fire. So the big fire always wins. It keeps its characteristics of spot fire. You don't know about it later on. So the other thing that happens is in going around tidying up the perimeter is that if the points are now further than 1 cell distance apart, we'll insert additional points around the perimeter. So these points don't actually last. So you don't have one point on the fire perimeter that you actually trace over the life of the fire. They're really just a construct of outlining the perimeter. So we're adding points and we can take points away. So I think I said that, so the tangles are a function of the Huygens spread algorithm. We add the extra perimeter points. And then finally, we have a dynamic time increment that we determine, and that time step is basically determined by how fast the fire is moving. So the range of time steps can be from basically 1 minute up to a maximum of 20 minutes. What we're looking for really is, with the maximum rate of spread, which is usually the head fire, that it's crossing about 5 cells. So if we had 200 metre cell size, then it would be the period of time that the fastest part of the fire might go 1 kilometre. But if we were using 100 metre cells, it'd be 500 metres. So it's proportional to the cell size or the resolution of the data, input and output data. So once we've got that new time step, we go back and basically repeat the whole process again. So and the fuels, the weather and the terrain are all reassessed under the new conditions. We look at the weather again, we look at the new fuel, terrain and so on, and we go back and redo all the calculations again. So to a lot of people, PHOENIX is this. It's the computer interface, but really we designed this as a test harness for us to be able to interact with the core PHOENIX executable calculation module. But to a lot of people, they still see this interface. So within the core, you can use it in many different ways. So don't get confused between the user interface, effectively, and the core fire characterisation model. So we've had some, this when you first start up, you've got to, of course, accept that all liability, that don't take any notice of these and don't rely on it for major... Is anyone from Tasmania here? Sort of. Don't rely on the outputs and all the rest of it. And it does require someone with plenty of fire behaviour knowledge to use it. It's just another tool in the toolbox. It doesn't actually provide an answer, which is a real risk of having something that has a big red, go back here, the big red button down the bottom. That gives people, that's the big red button to the big black box. So it's potentially quite dangerous, and that's why wherever I can, insist that a fire behaviour analyst uses it rather than someone who hasn't had that training and experience. But we've had some useful input and discussions from the US Forest Service. We use that for part of the wind modification across the landscape. We use Jason Fodder's mass conservation model to work out wind multipliers effectively across the landscape. Mark Finney has helped us considerably in the early days, I guess, in terms of some of the structure of the way we've set it up. And what's his name, Bryce and Cordy Teamster has certainly helped us with some of their experiences from the development of Prometheus. So we've certainly had considerable support and help with this. Given the time, I might skip over this. We're just going to go through a run of what it looks like and so on, the interface, but I don't think we need to look at that. So as I've already said, the grid cell size, it's not because we're actually running it as a CA type model, a cellular autonomous model. The grid cells are providing us a mechanism to store input and output data, and that's what you can then put in a GIS and analyse it. So the cell size, we recommend you shouldn't go below 90 or 100 metres, because you're starting to get below the scale at which the models make any sense. You can run this at 5 or 10 metres, but you then need to be having the weather at that sort of temporal resolution. You need to have much better spatial fuel data and so on. It will run at those levels. It's designed so it'll run at any scale, but you need to be really careful that you're not getting artefacts of fire behaviour by running it at 10 metre resolution. when there's an assumption that you've actually got a proper fire front. And if your fire front's only 5 or 10 metres wide, it's not going to behave the same as if it's 5 kilometres wide. So the underlying data may well be a 25 or 30 metre spatial resolution, but what we do is effectively average that out. So if we've got an area, for example, that might have some forest and some grass in the same area, we'll area weight the amount of grass and the amount of forest in that. So if we capture some grass in our 200 metre cell, then we'll capture that. We use a process called cell crawling. Well, that's what Derek calls it, which is basically one of the problems we saw with some of the other models was that they basically said that, okay, in this time step we go from this point to the next point. And the problem with that is you can jump over some really important information. You're assuming that everything between one point and another is continuous, which is not true. So what we do is, even though we might have a time step of, say, 5 minutes, we will go to the boundary of our next cell, do our calculations, work out how much time we've got left, then go to the boundary of our second cell, see how much time we've got left. So we capture all the spatial data and the temporal data in between our calculation points. So we can get away with a longer time period for doing our calculations because we're still capturing all the spatial underlying data. So one of the things we've included in the model is a rudimentary sort of fire suppression algorithm. And this is a fire in Victoria showing on the right-hand side we've got no suppression, left-hand side we've got suppression. That little green polygon that came up is a line scan that was done at a particular time. And the reason why we're so keen to have some rudimentary suppression in there is in a lot of southeastern Australia at least, suppression plays a major role in the final extent of the fire. And here's an example of where if you model it, see if I can go back, if you model it without the suppression, you get a much larger area affected. But we know in an area like this there's going to be quite active suppression, so we're trying to capture that. And again, it's a dynamic process. We look at how intense the fire is, how steep the terrain is, how dense the vegetation is, and for different types of, so whether it's hand crews or whether it's a dozer or whether it's an aircraft, those restrictions are dealt with differently. But we can do that in a dynamic modelling environment like this. So as I say, each point around the perimeter is treated independently. So that's suppression. What we can do is, we've got a sensitivity ability here, so we can take the wind as it's been reported to the nearest 10 degrees, but what happens if we change the wind by plus or minus 10 degrees, which is within the bounds of most of our observed data? How different does the result become? Well, one of the nice things about having it in a computational environment like this is that the time cost of looking at those alternatives is not that great. So here we see a mixture of forest and grassland, and it can make a huge difference to the final output if you change the wind direction by a few degrees. So another one in terms of, well, is it natural grass, is it grazed, or should I be eaten out? It can make a big difference. And it's not just about necessarily the 20% difference between natural and grazed that you might have, but it's also about the interactions that are going on in terms of the spotting, in terms of the progress and development of the fire across the landscape. So at least in a modelling environment like this, you're able to do a bit of a sensitivity analysis effectively. So this is a deep lead fire up near Stawell, if any of you happen to know that. And the same with curing. Curing can have a huge impact. Andrew Sullivan sort of showed us some graphs early on about the effect of curing. Once you get above 90%, it's not so important, but below 90%, it has a huge impact. And there's, I think, a need for some, I know there's some work going on looking at the way in which curing affects fire behaviour. The curing we see from a satellite compared with what the fire sees, I think is a major issue for us. It's a major difference, and often we classify fuel as being fully cured, and in reality it's probably only 70 or 80% cured. we go for the worst case. This is just a static image showing the difference between having the spotting mechanism turned on, if you like, as distinct from just trying to do a spread process, assuming the Earth's flat and well, not the Earth's flat, assuming that there's, you just have a frontal spread rate, and it can make a factor of 2 or 3 difference in the final extent of the fire. And it relates very well to some of the observations that we've got from Black Saturday and any fire for that matter, where the front is not always just a nice coherent flame zone. We actually have quite a bit of spotting going on, and we've seen that video from McCorkle 3 times of it in the last 3 days. I show it all the time too, I love it. But it shows the fire front is not just a line, it's actually an area. And when you get into large scale events like this, it's a massive area. It can be 5 or 10 kilometres that we're talking about, and that's what catches people out. So if we're not capturing that in our fire behaviour model, there's a problem. But we can't capture that unless you've got the scale of the fire involved. So it's not just about the fire line width, it's also about the amount of convective heat that's coming out. This is an exaggeration of the spotting process here. This is from Black Saturday. But what we've got here is a simulation of the spot fires, wrong mouse, from Pine Ridge Road. That was a mistake. So Pine Ridge Road, which is one of the areas where there was quite a few fatalities and a lot of houses lost. If you've got really good eyes, you might see some red dots there, houses that were destroyed. But if I just stop it at that point there, you see a lot of these fires on the lee slope of the hill, they're actually coming back up to the main fire. So the spread of the fire is coming from left to right, but there's certainly areas within this fire that are progressing in the opposite direction. And if we're not capturing that dynamics, then we're not going to be able to adequately quantify the impact of the fire across on houses and across the landscape. I'm getting a bit of a wrap up. So by able to do tens of thousands of computations of fire behaviour here, we've been able to look at things, Andy mentioned this the other day, in passing, apart from his fires around his house, where we look at the protection of biodiversity values, water systems and houses, and how can we manage our fires across the landscape, and what benefit do we get from that, and quantify it. The new code of practice in Victoria, the first chapter is about risk-based bushfire management planning, and that's been partly made possible by the PHOENIX RapidFire system. We've been working with power authorities and water authorities to look at where they best make an investment of their hundreds of millions of dollars in their network as well. We can look at where, so this is, we can look at some detail where it's coming from. We can redefine what the wildfire interface zone really is. Rather than the wildfire-urban interface, we don't want to know how far away from the bush we are. We want to know how exposed are we likely to be to a bushfire. So this is some work that I'll be talking about a bit later on, but you can see it's asymmetrical because fires aren't symmetrical and the weather systems aren't symmetrical. We can look at the fire proneness of the landscape when we light tens of thousands of fires across the landscape. And we can also look at fire severity, really important for biodiversity impact and water quality impact. And if we compare some of our field observations with what we get out there, it's not too bad. Much better than just mapping the scorch or crown loss of the overstory. So just to finish up, I guess the PHOENIX RapidFire model is a model in its own right. We try to capture a lot of the concepts that we know about fire that have been difficult to quantify, but they need to be better parameterised. The results are highly dependent on the inputs that go in. The graphical output is really important, and we spoke about the complexity of some of the modelling things. The visual assessment of fuel, the visual assessment of fire impact is a very powerful way to deal with really complex data, and we still need a lot of validation. I think John Marsden-Smedley said he did a bit of a test after the Tasmanian fires. You around? Where are you, John? And I think it performed reasonably well. So, but we need to do more of that. In terms of future directions, we need to basically verify what we've done with the convective part of it. We're looking at incorporating a dynamic wind reduction factor, so we're doing some work on that at the moment. We need to train the users better to use it, more detailed fine fuel, moisture and availability, improved asset impact models for the vulnerability side of things. So thank you.